Ah, no, no metí muchos conceptos técnicos. Es un poco plática a nivel un poco más superficial. Entonces es muy entendible en general, público en general. Hay algunas pequeñas cosas técnicas que no profundizo mucho y más bien lo que quiero mostrarles es eh, la aplicación del concepto. Claro, sí se puede hacer mucha investigación muy básica o investigación aplicada, pero lo que me interesa más bien es que vean eh, las posibilidades de aplicación.
Entonces, casi no la estuvo porque la primera que tuvimos, igual de 2017, hablando de electroquímica, fue bastante técnica, así que la mayoría sí nos quedamos medio apantallados. Nada más los químicos estaban bien emocionados. Pero bueno,
No, y además electroquímica es complejo. Si no tienes una, o sea, también para químicos inclusive.
fue llegar.
Sí.
Thanks for joining us this talk for the STEM week. I decided to be here, our speaker, and be respectful, finish the phone and talking. So let's make quiet, and if you need to get out of the room before the talk ends, please do it quiet. So today we have Dr. Francisco Rodriguez Valadez. Dr. Francisco Dr. Francisco holds a Bachelor in Science in Biomedical Engineering from the University of Aguascalientes and a Master in Science in Biotechnology from the State of Irapuato. He has a Master in Science Innovation for Business Development and a PhD in Chemical Sciences from the University of Guanajuato. Currently, Dr. Rodriguez Valadez serves as Principal Researcher at CDTech, where he leads groundbreaking research on microbial fuel cells as sustainable alternatives for water treatment and energy generation, as well as waste valorization under the circular economy framework. Through his career, Dr. Rodriguez Valadez has made significant contributions to science and technology. He has been awarded 3 patents and models.
¿Alguna de estas aguas está usada? ¿Se puede usar?
Approximately 40 million Mexican pesos. Also includes 72 PCR index articles, 1 book, and 4 book chapters.
Sí.
Dr. Rodriguez is a level 2 researcher in Mexico National Research System SNID from 2023 till 2027. Has also been mentored around 6 PhD students, 19 Master in Science students, shaping future generations as scientists. Please join me in welcoming Dr. Francisco Javier Rodriguez Paredes with a big round of applause.
Thank you very much. Can you hear me at the back? Okay. Thank you very much. First of all, I would like to thank University of Arkansas for the invitation, Professor Liliana and Diego. I work at CDTech. CDTech is a public research center located here in Querétaro. CDTech is a part of the new Secretary of Science and Technology. And now I would like to share with you our experimental results about the use of a new concept, the use of microbial cells as a wastewater treatment system. So first of all, I would like to ask how much wastewater do we generate? We generate a lot of wastewater. In this document, has documented that in 2015, the wastewater generated around the world was about 380 trillions of cubic meter. That's a lot of quantity of wastewater. And you need to add the industrial wastewater that is not considered in this value. And also, this quantity of wastewater will increase in the next years. It will increase 24% in 2030, and 51% in 2015. Talking about wastewater treatment, according with this document, in 2015, only between the quantity of wastewater that was untreated, that is the water that is not treated, was between 30 and 92%, depends on the country. In low income countries, the percentage was 92%, and in high income countries was 30%. This percentage will decrease because of the installation of water treatment processes, and in 20 there is expected that this percentage decrease to percentage between 15 and 46%. Well, that implies that some facilities where is going to be installed in the next years. Also, as you say in the document that was printed by the European Investment Bank, there is a change of the view of the wastewater. We are accustomed to see the wastewater as a problem, but according with this document, the wastewater must be a resource than a problem. That's because we can obtain some benefits from the wastewater. For example, clean water, biogas, or energy, and also we can obtain nutrients. So this is a change of the point of view that is very interesting. On the other hand, we're accustomed to hear about global warming, and there is a serious problem in our days. That's because the production of CO2, and that's why it was implemented the 1.5 centigrade pathway. There are some strategies in order to maintain the increase in the water of the planet only 1.5 centigrades in 2015. That's the goal. So we are implementing so many strategies in order to decrease the CO2 emissions. One of these strategies is the implementation of alternative energies, according with the International Renewable Energy Agency. In 2030, 68% of the electrical energy must be produced using alternative energies. And in 2015, 91% of the electricity will be produced using alternative energy. Well, coming again to the problem of wastewater, there are so many processes to process the wastewater, to treat the wastewater. But one of the main problems is the use of energy, because this process requires energy. And some of them, for example, in the case of the activated sludge process, that it is the most common process all around the world. The cost of the treatment is associated with the cost of the energy, because between 70 and 80% of the cost of the treatment is associated with the cost of the energy required to that are required in the geological reactor. And this is important because this is the most popular wastewater treatment process in all the world. So that results in high operational cost. And for example, in Mexico, there are some wastewater treatment plants that are abandoned because they don't have the budget to operate. And that's a problem. We have health and environmental challenges. So the question is there another option, another friendly option to treat the wastewater? And the answer is yes. I would like to show you a new approach that we are developing, and a disruptive approach that is called microbial cells. The microbial cell is a bioelectrochemical systems that can treat the wastewater, that is, can eliminate the contaminants in wastewater, but also produce energy at the same time directly. That is, if you have wastewater, you collocate in contact with a reactor. The MPC is a biological system, so you have a microbial population, and the products are clean air, save energy, because this process does not require a lot of energy. It's not intensive in the use of energy. And in fact, this process can produce a certain quantity of energy directly from the process. Comparing this new concept of microbial cells with the typical activated sludge process, for example, the activated sludge concept was developed in 1914, and since then it was implemented in some process, in so much applications in the field. And since 1915, it is the most popular wastewater treatment process in the world. Now, indeed now, it is the most popular. And in the case of the MPCs, the concept was discovered about 1915, but until 1990, there is going to begin with the research about this concept. And the first pilot scale installation using MPC were in 2010, 2015. Talking about the scientific impact of the microbial cells, as you can see in the last years, the number of publications increased. For example, from 400 in 2010 to 1,400 in 2021. That is a big increase. Talking about countries, the country ranked in number one that is doing research in this concept is China, followed by United States, India. Here in pink color, we are in Mexico. It is supported about 186 scientific papers. Well, this is the concept of microbial cells. This is a bioelectrochemical reactor. In this case, we collocate the wastewater in contact with a biological, microbiological population. And this is a typical chain of MPC. There are the two compartments and two electrodes. In the anodic compartment, we have the anode. In the cathodic compartment, we have a cathode, and that are separated by a membrane. A biofilm grows on the surface of the anode, and then this biofilm degrades the substrates contained, or in this case, the organic contaminants contained in wastewater, produce electrons as a byproduct. The electrons are transferred to the surface of the anode, and then in the anode flows through an external circuit to the cathode, and in the cathode there is a reduction reaction using the electrons produced in the anode, and the circle is closed. In this way, we degrade the contaminants in wastewater and also produce an electrical current at the same time. Comparing this alternative with the traditional wastewater treatment systems, the microbial cell remove the contaminants. You can see the positive and negative effects. The microbial cells remove in efficient way the contaminants in wastewater, consume low quantities of energy, generates a lot of energy, or generates energy, not a lot, generates energy. Generate low quantity of sewage sludge. It has low footprint, carbon footprint, and requires low quantities of land. Compared with the typical waste activated sludge process, that it is efficient to remove the contaminants, but the problem is that it requires a lot of energy because of the aeration, generates a low quantities of sewage sludge. It has a high carbon footprint, and that's a problem. Okay, I would like to talk about our experiments in the lab. We are working with the MPC concept since 2012. We have built several prototypes at lab scale. Those are the first prototypes. This is a typical H type cell. We will have two compartments. This is the anodic compartment with the electrode where the microorganisms grow. And in the other side, in the left, there is the cathodic zone. There is the cathode when we apply air to supply the oxygen. Then we have obtained a grant from EconoSeed for about $100,000. Later, we designed some other membraneless MPCs, and in 2019, we have designed and built this prototype. This is a membraneless microbial cells that we have used to treat about 1,000 liters per day of real. In this case, we have used real wastewater. We have obtained the patent of this design. Then we changed the concept. We now are using the ceramic microbial cells, and in 2023 we are working with energy production. In this case, we have evaluated this system as a wastewater treatment. It works well. In general, this system removes between 80–90% of the contaminants. That it is good, because this is the typical percentage that can be obtained with any biological system. So as a wastewater treatment, this system works well. But the problem is the production of energy. Okay, this is a typical MPC. I'm sure that you have seen this ceramic before. We have used it. Have you seen the carrito that is used to prepare beverage in public places and in public parks? We have used this container as a membrane. That was the idea, because we tried to show that it really works. So we have chosen this material. This is a ceramic, local ceramic, and the ceramic, at the outside we collocate carbon felt. This is a conductive material. And inside we have collocated also carbon field. And this is the typical cell with the ceramic, the anode, and the cathode. Well, we have experimented with this MFCs collocating several MFCs in a model. For example, in this case, we collocated eight MFCs in a model, and this is the most important tool when we are evaluating the performance of the MFCs. This is the polarization curve. We obtain this curve collocating different physical resistance in the system, and then at the equilibrium we measure the voltage and the current that we generate, and with applying different different resistances, we can obtain this polarization curve, and also we can obtain that red curve. That is the power curve, and it indicates the highest power that can be obtained with this system. This is the important data. If we change the arrangement we change the cell, we can evaluate the power that we can obtain from this arrangement. That's why it's very important. We change this arrangement. In the last case, we have collocated the 8 MFCs without any separation, and then we use a separation. Each one of the MFCs was separated, and we also evaluate the power production. And so we modified the arrangement of the electrodes, and this is the initial power obtained with the initial arrangement. We modified the MFC, and we have obtained a better performance. In this case, the power generated is 4 times the initial value. This is the experimental setup. We have collocated the MFCs in a critic model. We collocate 8 MFCs in each one of this model with different arrangement, because we're trying to evaluate the effect of the arrangement on the performance and on the energy production. We feed synthetic wastewater that we prepare in the lab, and this wastewater contains about 300 milligrams per liter of COD. COD is a chemical oxygen demand, and we can measure the content of organic contaminants we use in COD. And in this case, this value is typical of any sanitary wastewater. That is the wastewater that we generate in our houses. Then we try to use the energy. As you see, we can turn on this LED decorative system, turn on some LEDs. This is an electronic device to charge a battery. We can charge lithium batteries to preserve volts. And also we can start small electric motors using the energy produced by the MFC systems, by the MFC system. This is a second video. We have proved to light on several LEDs with different power requirements, because we like to prove the use of the energy. And as you can see, all of them were lighted on. And this is a commercial LED lamp that you use in your house. This is the last video. Then we try with a commercial LED lamp. As you see, we can like on. When we disconnect the wire, the lamp light off, and we're using in reality we're using the power generated by the system. There is no switch in the back. Okay. We also have made many experiments of scale because we feel that it was very interesting. So we have built this system. This is a low cost microwave fuel cell stacks. We have used the same emphasis arrangement. This system is designed to treat 450 liters per day of wastewater, real wastewater. This system is now working in CDTech, treating the wastewater produced by the center. The CUD values are between 300 and 400 milligrams per liter. And the area required to this system is about 4 square meters. We have collocated 6 MFCs in a model. As you can see, the model is a plastic box that we can get anywhere. This is a local system, remember? And we have sanitary PVC piping. So it's really a local system. We have collocated the emphasis inside the module, and then one module on the top of the others. And finally, we have a stack with 6 modules. Then we fit real wastewater in the top of the stack. And the water goes through the first module, the second, the third, and so on. And the effluent is in the bottom of the stack. Each one of these stack was designed to treat about 110 liters per day. And this is the value of COD removal. When we get the steady state, the removal is about 70–80% of the COD. That this is a typical value of any wastewater biological wastewater treatment. That is, it works well as a wastewater treatment. That's using real wastewater. And the quality of the effluent is near the Mexican norm. Okay, we have also developed a system to obtain the electrical parameters. We every time we are measuring the voltage, the current, and the power generated by the systems. In this case, you can see that the voltage generated in the system is about 4 to 8 volts, and the power was between 4 and 12 milliwatts. And now the challenge is to recuperate, to obtain the energy and not to lose so much energy in the system. The average in voltage that we can obtain with this system is about 6 volts, and the power is about 8 to 10 milliwatts. Another system that we have built up at scale is a combination of the emphasis with wetlands, using real wastewater with the same COD, and we have installed this wetland in a metal container. We have collocated 21 MPCs and 18 plants, different plants. This system was designed to treat 140 liters per day. In this case, when the system reached the steady state, the COD removal is about 80%. That is, we can clean the water using this system, combining MPCs and plants. We're doing basic research, but we're also doing applied research. This is the scale of the maturity of the technology that was designed by NASA. And in terms of technology, we think that we are in the middle, about TRL 5. That is, we have done pilot scale plant experiments with real conditions, in conditions that is centrally in real conditions. Thinking about our projects or about the projects that are doing our students, there are so many things that we would like to evaluate. For example, to improve the electrical connections, we have a loss of energy all around through all the system. We need to improve this issue. We're working evaluating different configuration of MVCs. We are designing and making our own ceramic membranes. We are combining MVC with wetlands. We are working with the recovery and storage of energy. We are doing so many things about the use of different new materials as an electrode. For example, this is the case of Raquel. She is working with the MPC wetland system. As you can see, in this case, we have separated the MPC from the body of the wetland. That is because we would like to recover more energy. And we are trying different arrangements in order to see how the system or the performance of the system. This is the project, the Jorge's project. He's working with the development of electrodes from organic waste. He's using orange peels to prepare activated carbon, and then you use this activated carbon to prepare electrodes. This is a project of Roberto. Roberto is working with the design of the MPC in order to develop a scale-up arrangement or scale-up configuration, because this is a big problem. It's one of the biggest problems in the case of the MPCs. And as you can see, the COD removal is quite low, but there is no problem because we can connect some of these units in series. Finally, this is the project of Fernando. Fernando is working with the production of membrane using different network clays. And this is the system of MPCs at level scale. And this is a typical response of one cell. You can see the voltage generated each time that the cell was filled. In all cases, the CO removal was between 80 and 95%. We have received students from different universities, en Querétaro, San Juan del Río, Corregidora, Aguascalientes, Anáhuac University, from different institutions. And we have academic collaborations with some other institutions. We collaborate with Dr. Yanis Gueropoulos of the University University of Southampton. She is one of the most recognized authors about NPCs. With the Veracruz University, Querétaro University, and with the Clean Tech Consortium of the Royal Academy of Engineering. We have published several scientific papers about the use of different electrodes, arrangements of the cell, about the thermodynamics of the process, diffusion of the electron, that is basic and applied research. And we have also had some efforts in innovation. This project was incubated at the Tecnológico Monterrey Incubator. This project was elected, was chosen to participate in the program of Leaders in Innovation Fellowship offered by the Royal Academy of Engineering. And this is a training process about the acceleration of base technology entrepreneurship. And in the final stage, we have presented this project in London in 2023 at a committee. This training program was offered by Oxentia. Oxentia was the belonged to the Transfer Technology Office of the University of Oxford. In 2023, we have participated in an open innovation call with Bimbo. We have worked for about 10 months in order to have a project to develop. They accepted to finance the project, but at this time, this project is in pause. And we have elected as one of the best 20 projects in the Biotech call. Thank you very much. Here's my email. If you would like to know more about this topic, if you have any answer, or if you would like to visit CDTech, please contact me.
So if any questions, I remember you will chat the wrap-up for those who participate. So is there any question for Professor Francisco? And how much amount is
Yeah, to maintain the bacteria is really easy as such biological system. If you have the conditions, there's no problem. That is pH, there's no toxic substances. In this case, this bacteria does not require oxygen, so there is not so much problem. And the second was?
How much or how is the amount that you need, for instance, to lit the lamps that you show in the video?
It depends. It depends of the requirements. For example, the last one requires about 12 volts. No, okay. That's very interesting question, because we need to generate the power in a combination of voltage and current. It is not necessary, so it's not only necessary to take care of the voltage. We also need to combine the voltage, a minimum voltage, and a minimum current. For example, in the case of commercial lamps, they work well with 12 volts. The LEDs needs 1.5 to volt. Oh, maybe, yeah. Yes. But the challenge is to obtain the energy in a useful way.
In how much time does the process have to be on to generate the electricity or well the light?
Yeah, those are continuous process.
Okay.
Yeah. We're talking about 1 day of retention time. Yeah,
Okay.
marvelous. Thank you so much. Thank you. You're welcome.
What are the most common microbes that you tend to have in microbial fuel cells?
Yeah. The most known genera is Helicobacter. Helicobacter. But in this case, we have no pure culture. That's very difficult. In talking about real condition, it is very difficult to use pure culture. In fact, you set a pure culture, then the microorganism, there's an evolution, and finally, this is I feel that it's a consortium. In our case, we have identified Pseudomonas. And because it is supported that Pseudomonas has the property to transfer the electrons. In this case, with the microorganisms, it is relevant that the microorganisms can transfer the electrons. Those are called exoelectrogens.
And have you thought of doing microbial transformations to increase that transfer?
We are not doing that at this time. Yeah, it's very interesting because we talk, there is a parameter that is called Coulombic efficiency. That is the relationship between the COD removal, of the current, and the COD removal. That is, if you have a better efficiency, it means that you can produce more current when you eliminate some quantity of COD. But the Coulombic efficiency depends. In this case, is so low, about 1%, 2%, 4%, 5%. And the consequence is very interesting because it is desirable to have microorganisms that produce more energy.
I have a question, and it is about the use of the ceramic.
Yeah.
Is there any reason why you use only that type of ceramic containers, or are there like more efficient ceramic ones? Or
No, we have this ceramic because we would like to prove that it really works.
okay,
Because as you see, it's very simple. You can get anywhere. So I buy some. Finally, I get one of them in six pesos.
at most.
Yeah, and it's quite low. But there is a challenge. This is the beginning. Now we are making our own ceramics because we need to control some variables. The membrane determines something. For example, diffusion of the protons, diffusion of ions, diffusion of oxygen, and those factors affect the performance of the cell.
Perfect. Thank you so much.
Hi, thank you. What are some of the challenges you're facing regarding storing the energy? Like,
Oh, we have a lot of loss of energy. It's very simple. because of the material. Now we're using, at the beginning, we were using copper, but there is corrosion problems. Then we changed to stainless steel. But it has a lot of resistance. Now we're trying with titanium, and we're trying some materials. And the next challenge is how to. There is no problem with the production of energy. The problem is to collect the energy and to store the energy. And now we're trying to find a way to collect the highest quantity of energy, and then to store in a battery. Yeah? Now we can with that.
Thank you.
We have time for one more question. And if you have more questions, you can always ask Dr. Francisco by an email or by intercepting him outside.
Are you using any amplifiers or converters for your current in order to use the power collected more efficiently?
Maybe it's a possibility. Yes. No, at this time. It is. I think I will be trying that in the next. Yeah. That's because you can see that there are a lot of challenges, and we need to focus one by one. But it is necessary to look for the storage of the energy. That I think that it is the biggest challenge.
Well, everyone, that will be all for this talk. We want to give Dr. Francisco a gift for part of the committee and our sponsors.
Thank you.
Let's say goodbye with a big round of applause.
Thank you.
Our friends of Tienda La Paz. If not, you're free to go. If you have more questions, to Dr. Francisco, you can send an email or ask him outside. Thanks a lot to everyone. Goodbye.
Thank you. Hola.
Muchas gracias por la plática. Una pregunta rápida. Esta parte de pasar al agua, ¿hay algún